Hello, welcome to my channel. In this video, I'm going to walk you through question number 5 of our exercise. In question number 5, you are asked to determine the array factor of a suspended dipole antenna. And this is the Hertzian dipole antenna, the short dipole antenna. The antenna is placed above the ground plane. The ground is assumed to be a reflector. So underneath the ground there will be an image. Both image and the physical antenna will contribute to far field. The height of the antenna is D. The antenna is pointing vertically. So we are going to first determine the array factor. Secondly, we are going to determine the power factor. And finally, we are going to plot the polar diagram for the radiation pattern. And this is most likely the power pattern. Okay, so I'm going to switch you back to the okay, so I'm going to work it out. So first of all, we need to draw the three-dimensional coordinate and x, y, z. And somewhere above the ground, the height is D. We have an antenna, number 1, and this is the Hertzian dipole antenna, the short dipole antenna. And because the ground itself is the reflector, we expected an image to be produced underneath the ground. So this is antenna number 2. Both antenna number 1 and number 2 will contribute to the far field. So let's say we have in a very, very far field zone, we have an observer. The observer is very, very far away from the origin. Suppose the distance between the observer and origin is D. And is R, yeah. And the distance between the physical antenna and the observer is R1. The distance between the image antenna and the observer is R2. The observer will be very, very far away from this setting. So in this case, R1, the pathway R1 and R2 are essentially parallel. arrow 1, arrow 2, and arrow are essentially parallel. So in this case, if there is an angle of elevation in here, theta, then we expect another angle of elevation here, also theta. And the angle of elevation for the image antenna is also theta. And in terms of magnitude, we can approximate R1 is more or less equal to R2, more or less equal to R. In terms of phase, we expect R1 equals to, R and R1 are not exactly the same. As you can see here, there is a difference. How much is the difference? Depends on this value. So if this is the right angle and this is also theta, then we expect d cosine theta as a difference in terms of the physical distance. So R is larger than R1 by how much? By d cosine theta. Similarly, for R2, we can use the similar definition. In this case, R2 is longer than R1, but by how much? By this amount, d cos theta. So the next thing that we are going to do is to work out the total electric field as detected by the observer. The total electric field as observed in the destination is the combination of two electric fields, one from antenna 1, the other from antenna 2. And we are going to use the formula that we have learned from the magnetic vector potential, from the chapter on magnetic vector potential. So this is the formula that we are going to use. At different distance, the electric field will be different. The far field electric field will be different. So in this case, what we are going to do is to work out the electric field contribution from each of the antenna individually. And in this case, E of 1 will be equal to I naught L and 4 pi R1. And then E J K R1 sine theta. And the electric field as a result of the image antenna is going to be similar but now in terms of magnitude, as we have already shown, they should be similar. So in this case, in terms of magnitude, we can say R1 and R2 are basically the same. So we can just bracket out this expression, and we can have shown R1 is equal to R, like what we have shown here. And we can, because both terms contain sine theta is the common terms for both expressions, and we have to bracket the expression here, E, J, K, R1, and we are not going to have shown the phase difference. If we do that, then we are not going to get anything. So now what we are supposed to do is to substitute these two expressions for the phase. The phase is going to be treated more accurately than the magnitude. This is the key point. So K R1 and K R2. So this is what we are going to get. And if you work out very carefully, you will get sine, theta, and we will get the common terms here. And we will get 2 cosine k d cos theta here. So this is the combined electric field. And we are going to use this conclusion to further develop derive. So this is part 2 of the question, part 1 of the question. The part 2 of the question is to plot the array vector, and let me make it clear. The array vector is here. The element vector is here. Okay, I hope this is clear enough. So the next thing that I'm going to do, I hope this is clear enough, right? Apparently it's not clear. It's not clear enough. Okay, this is the best I can do. Maybe it's too bright. Okay. Now, if it is clear enough, then the next thing that I'm going to do is to use this expression. Use the array vector, and we will plot the array vector against theta and see what we are going to get. So the array vector will be like this, and theta will be like this. So what we expect for d equals to lambda divided by 2, I mean 0.5 lambda. This is what we are going to expect. And this is going to be 0. This is 1. And if you use a shorter height, then this is what we are going to get. Okay? So this is part 2 of the answer to the part 2 of the question. Part 3. Part 3 is to determine the power. The normalized power is equal to the square of the normalized electric field, which is sine theta square cosine kd cosine theta. So this is the answer to part 3 of the question. Part 4 is to plot this out. depending on the value that you got for t. So 2 pi and then t. If you put the Argand diagram, if t is equal to just 0.1 lambda, then we are going to expect like this. Remember, theta is and if t is pi lambda, then what we are going to expect is similar. And if t, the height, is equal to 0.5 lambda, we will expect a side loop here. Okay? Okay, I hope this is clear enough. If you have any question, please leave your question to the comment section of the video. Thank you.